Sonodynamic therapy (SDT) is a new modality using ultrasound to activate certain chemical sensitizers for cancer therapy. Effective SDT needs the assistance of sonosensitizers. At present, the most widely used sonosensitizers in SDT are typically porphyrin and their derivatives, but their practical application is hampered by their inherent drawbacks, such as hydrophobicity and fast metabolism. In this work, we first found that the MOF-derived mesoporous carbon spheres containing porphyrin-like macrocycle groups could be used as an efficient sonosensitizer for the augmentation of sonodynamic cancer therapy. This particle, we call it PMCS, is synthesized by carbonization of the ZIV-8 metal organic framework. SPSC have verified that this central metal zinc in PMCS is in the similar coordination chemical environment as organic porphyrin zinc. Interestingly, after a comparative study of SDT enhancement of PMCS with organic porphyrin molecules and amorphous carbon nanospheres, we first found the PMCS augmentation effect is highly related to the porphyrin-like macrocycle. The higher homolomal gap of PMCS is believed as one of the main reasons for the efficient separation of electrons and holes and ultrasound irradiation. Further, the generation of highly cytotoxic reactive oxygen species was enhanced, including singlet oxygen and hydroxyl radicals. Excitingly, singlet oxygen generation efficiency of PMCS increased by about 200%, and the ultrasound irradiation much higher than that of amorphous carbon nanospheres. To investigate this augmentation mechanism, oxygen-hydrogen bond of soft water at PMCS is calculated via a density functional theory, DFT modulation. We found this bond length was slightly longer than that at organic porphyrin zinc, suggesting that water molecules absorbed on the surface of PMCS are easier to be activated and generate ROS than that of organic porphyrin zinc. Another advantage of PMCS is their high porous structure. It also provides more cavitation nuclei. We capture this phenomenon by a high-speed camera. We found that the number of cavitation bubbles in PMCS is greater, and the size of the bubbles expanding to their maximum volume in PMCS is larger than that in water. Our in vitro and in vivo experiments also validate the potent anti-tumor efficiency of PMCS under ultrasound irradiation. We believe this work will deepen our understanding of mechanism of sonodynamic cancer therapy based on MOF-derived porphyrin-like carbon nanostructures.